This is the initial inspection of the Heathkit impedance bridge IB-2 alpha that I've received. You can see I've already started to do some cosmetic testing on the unit. Wanted to make sure that this initial coating that I saw, I'll try and zoom in here, and this is what the texture looked like. I wanted to make sure that this wasn't actually the paint, especially in a test equipment like this. I have a lot of Heathkit stuff that sit there at 90 degrees and you don't really see the texture of the front face. Something like this that has a bit of a camber to it becomes increasingly important. Happy to say, and it looks terrible in contrast, obviously, that none of this affected the paint, and I did a nice cleanup and then used a little bit of the Meguiar's spray wax, the polymer that I use, and you never get a really good picture, but you could see that the paint under there is absolutely perfect, right? So we're looking at a nice finish. I did another piece on top. You could see like there's almost no reflection on the top portion of the unit there, and then right here it becomes nice and clear. You could see my cables hanging from the test set in the corner here. The top piece was not done with the amount of cleaning that this portion was. We're just testing. Another test piece was done here between the Q on the dials here, little checks and what have you. Also, a small piece of the meter to make sure that the condition of the meter was good. A couple of stress cracks here that you always see on these meters. The missing screw is actually in the meter. I just need to open it up and reattach it. The meter itself does deflect. It's good. A couple of these are chewed up a bit. These are relatively easy to find, these knobs from Heathkit, so I'm not really worried. This one and this one. Some knobs do interesting things. I noticed, like meter and shunt on DC snaps back, so it's spring loaded. I haven't fully read the manual yet. This AC set 0 clearly is outside of the prescribed lines. I haven't opened up the back of the unit yet, but things seem to be free moving. No causes for concern yet. We're going to go through this whole piece of gear, very carefully and make sure everything's doing what it's supposed to. I checked the range of motion on these. It appears okay outside the fact that they're all a bit off, but not to worry. So we're going to get in there and take a look around back. The plug itself was connected. It was cracked in half. It was Bakelite. For the purposes of this, I actually went and glued it back together. Next time I get an order out there, I'll order me a nice 2-prong. But for testing purposes now, I go into an isolation transformer anyway. I'm not really concerned about the AC. I don't plug it into live mains and stuff, so not to worry. But really cool. There it is, sitting here on the table. Looks like it will clean up very nicely to showroom quality. A couple of nicks here and there, not too concerned about that. It gives it a little character. But it matches the same vintage, the same lineage as all of my other Heathkit equipment, same type of things going on here. So very cool indeed, right? So I got that. I got that up there. I got the other Heathkit stuff there. Not an enormous collection, but a nice collection and growing. So there it is. As I pull back the cover, I often wonder how after 50 years or something like that, a large piece of solder ball can be laying on the bottom of this unit. I mean, it may reveal itself. I don't know what it was connected to. It could tell the tale of somebody who put this together really quickly and didn't solder something right. Maybe the thing never worked. I guess we'll find out when we go through the manual. But these are the things when you open this stuff up. It could have been opened last week. It could have been opened in the 1950s, but big glob of solder just fall out the bottom of the unit. But this is Heathkit. If you spend time working on Heathkit stuff, this is the stuff that you're going to find. But we're going to pull this cover back. With the size of this cord, I don't know if we're going to be able to pull it through, but we'll get it out of the way. But nothing crazy in here. Some dust. That's about it. This unit had no fan, obviously, so it didn't collect an appreciable amount of dust. There was no top ventilation to have dust flow into this unit. I've got the unit up sideways here. It is divided into two separate sections here. We have this metal shield that separates the top from the bottom. We're looking at the top right now, so all the magic happens right here at these posts, essentially. And the tubes look original. These are the Daystrom labels right here from Heathkit that would have been provided. I see a filter cap here that's probably no good. The interesting things are the capacitors and the resistors that, by even today's standards, are impressive. We're looking at 0.5% tolerance on these. No wire is used where appropriate. We're looking at extremely thick bus bar with no coating, as obviously not to induce any capacitance or inductance on the circuit. So extremely overdone transformer here. As you can see, no stone unturned. I mean, we're looking at look at the numbers on there. Half of a percent values, and right down here, look at this. This is a made in England wire wound multi-can cap. This is for the dial in the front, which obviously we'll have to take some measurements on, but we'll accept it right now. This is Culvern Limited, and this is the main dial that we use, whatever it may be called. We also have this a couple of these 10,000 picofarads, 0.5% in the plus or the minus. The other one I can't read. I'll assume that its tolerances are close to that, right? So aside from this filter cap, which actually serves the bottom of the unit, not the top, we'll say that there probably won't be a whole lot of replacements here, just some tube socket cleanings and a whole lot of checking, right? And especially cleaning all of these gangs right here, that these multi-sectional gangs, right? You can see there's some accumulations on there that we could clean out, right? But if you look on the bottom, you know, it's your typical Heathkit conundrum here. We've got some paper electrolytic capacitors down here that need to be replaced. These can be checked. These, I don't have to shotgun replace these. Obviously, you pulled it right out of circuit. Check the value. Can it support 600 volts? If it can, we can leave it in. This is not audiophile grade. I had mentioned this particular switch here had a spring action, and now we confirm that. We could see that it is indeed meant to be. It's ganged, except for the last value, which springs back. So, and as we open it up, we learn a bit about it, you know. So this is going to be a nice evening of replacing what needs replacing. This thing looks so original, though. I'll tell you, this is going to be one of those where we'll probably cut the can out of circuit, but leave the can in there for posterity, and put in some electrolytics here on the bottom, as to preserve the unit, because it's absolutely in original condition. But obviously we can't leave the cans running in there. We've got some Sangamo capacitors down here, and remember from the Dan Electro, those are time bombs. It's absolutely terrible. Other things going on. We have some interesting stuff here. It looks like a selenium rectifier over there. Generate some DC. There's some things going on here that we need to look at, because we don't see them in a lot of our equipment. So pretty cool. Let's investigate. See, type 47 lamp. So we'll have at least our heater voltages. Got that much going for us. We'll go through it. We'll get it going, get it running, figure out how it works, and then test it out. But when this is working, it should be really sensitive as far as getting us values for components and coils and what have you. So we'll get started. Very gently, I was able to get a razor blade under the perimeter of this case and pry it open without causing any damage. Be able to get those screws back in and tighten down, get the case back together without breaking anything. I'll be able to install that meter back in, which is a good thing, because the meter cost about $30 alone, which is about the price of a unit. Had I done this and broken the front plastic, that would have been cheaper, about $8 just to replace the front plastic. But I broke neither, so now I could get it back in the unit. Another piece solved. I haven't done any great deal of calibration. I brought it up solely on the Variac after doing some ESR readings on the capacitors. Definitely not where I want it to be, but determined it's safe for our purposes now. It's a Variac through isolation transformer and monitoring the current as well. It's current limited. And what I've got is from the documentation just going along. Didn't really understand the calibration procedure, but what I did was I took a 1500 ohm resistor and went through the procedure for simply deriving the resistance, went through all the steps, and it doesn't use all the features here. We're just getting DC resistance here. And sure enough, in following the instructions and balancing the bridge, I did in fact end up with 1K times 1.5, 1000 times 1.5 for 1500 did in fact balance the bridge. A lot of times when you know the resistance, there are ways where you lead yourself to the answer to the equation. So what I'm going to do is several readings over several ranges, prove out resistance. I know that the capacitors could definitely be replaced, and the AC is a bit dirty. I looked at it on the oscilloscope over there, so I'm not going to be doing anything with inductors or whatnot. No AC generator is going to be turned on inside this, but definitely want to see the resistor and capacitor stuff, see what that's able to do. So we'll take a look. So I've hooked up the Decade resistor box. I got it set for 50 ohms right now, set up here, right? And if I were to follow the instructions as it's set up, what I'd really actually be doing is setting it to 100 ohms, because 100 ohms would have the least amount of deflection from zero that points to the left, right? So obviously 100 is there and 10 is there, so 100 is the winner, right? So 100 would have a CRL number of 0 where it sits there. And you could see that it works, that if I bring 100 up to 0.5, right? Let me bring it there first. 100 to 0.5, you can see it sits at 0, and that would be 100 times 0.5 is half of which is 50 ohms. So it's correct, right? So that's 50 ohms of resistance. What I also found is this: if I take this and bring it back to 0, and I realize I got the light pointed at it, so I'm trying not to get the glare on there, right? And we bring it to 10, you know, now we're way off, right? But we could take the CRL, leaving the inner number at 0, and accomplish the same task. So now we have it at a setting of 10 ohms per value. The outer multiple is 5. So that's 5 times, and actually it's a little high. Let me turn that back to 0. Right there, it is in the middle. So now we have 5.0 times 10 equals 50. So 50 ohms balances out. We can see we have a reading of 50 ohms. So there's more way to derive the values, but according to the instructions, that's not the way they want you to do it. They want you to use the 100 and then do the 0.5 divide by 2. So I'm not sure why, but that's the way they want to do it. And this is on the 0. It's just that I've got the shadow because of this light I've got here in the back for better viewing. But so far resistance is looking good. But now that I got the Decade box hooked up, which is kind of cool because it's the same exact vintage and style, you can see, but I'll be able to test a wide range. I just got it plugged right into the top there. In further reading of the documentation, as I asked myself, how could this possibly become more precise? There is a instructional for the configuration of this knob right here, CRL. I'm not doing this because I do not have a precision resistor required to do this, but to illustrate the precision, what I was doing earlier in my demonstrations was, and the box here is set for 550 ohms, right? So just to talk this through, we're set for 100 ohm resistance DC, okay? And we're at 5, so we're at 500 and thinking would say that we're just under. So I turn it up and I approach, 550. And as I bring it in, 550 looks good, right? And I said to myself, is this really precise though, right? I mean, is it 560? Unless you really look at the needles, at 540, 550. So what I found out is once you get that ballpark reading, right, this scale becomes a percentage of itself, right, by flipping that meter switch from shunt to meter. So what happens is, and I can't do this with two hands, but just basically to show you, when I flip it to meter, I actually got it so close I can't really show you. So let's say it was at 540 showed the thing to be in the middle. When I flipped it to meter, it was off like that. So if you were able to hold it to meter and slowly bring it in, you would get it right on the money. Let's get to something like that. So it's 5. From the purposes of our scale, it almost seems as though it's right in the middle. Like I bring it down a little bit, and it's like you can't really tell. It's showing 570, right? So 570 amplified shows it's off by a magnitude, like maybe 40 on the scale. And as I bring it down to 550, even 550 shows it to be slightly off. So I bring it down. Obviously, if I were holding it, and doing this would be a lot easier. But right there, when we see that there's just a minimum amount of deflection at that point, almost nothing, we see the actual value is not 550, but we get something even more precise, which is a fraction thereof, which is pretty cool. So now I know what that function does, and now I know that we could really get extremely precise values worth revisiting. So I'm definitely going to have a look at that. But this is also 550 is the magical value used to set this knob. So all the internal resistances and what have you are judged by a resistance, 0.5% or what have you. 550 says that if that resistor were put across these posts and I were to flip this meter switch and this meter switch were to be exactly in the middle, aligned, this knob would actually be loosened from the screw post here and then adjusted outside of the circuit to lock down to 550, and that would set this internal resistance exactly what we wanted that to be. To make things easier, I went and took off this plate here and polished the plastic. It has a bit of a magnification to it too, which made it very nice. The first and most important thing here was evaluating these 0.5% resistors that sit behind this block here. This is the CRL multiplier. And make sure that this CRL is still good, because this is 0.5%. And really got to find out why that is and what's important about it. So what I did was I picked a value that sat right in the middle of all things, and a value that I turned out to be sat there in the 100 ohm setting. And that way we're only dealing with one multiplier value, right? We're taking this out of the equation. Good, bad, or indifferent, we're using this 100 ohm value. We don't care about any of the skew in between this. We don't really care about this skew per se, because we're not adjusting for this skew. What we're really looking for is this skew. So what I did was I set up my decade box and tested these values with the fluke and made sure the top two were some other stuff calibration. I did that 111, but you see the 149 all the way down to 949. And basically what I would do is I would bring it into play, starting at 149, and I would tune for this, not for 149. So I would get the value and find out how much it was off by. So 149 I would read 143. I would find it would be off by 6. And then I would switch the box to 249, switch this to 2, and then get the value and find out what 249 would read, and that would read 244. And then you would see the correction factor was 0.05. And you would find that as you would go up, and the only thing that you're really adjusting is the CRL multiplier, that as you go up, the correction factor seems to get lower and lower until you hit around 7 on CRL, and it becomes 0. 7 and 8 show no correction factor whatsoever. 749 on this set actually reads 7 times 100, or 7 plus 49 times 100, 8 plus 49 times 100. And then when you get to 9, you see that 9 actually goes in the other direction. So 9 reads 950 with a correction factor of 0.01 in the other direction. What this tells me is that when you have this dialed all the way up to 9, the higher the number is, the less resistors it sees in the circuit. And as it comes down, it adds more and more resistors in series, which makes sense when you look at the back of the box and you see these precision resistors here, right? And that's why stuff on 9 looks so good and deteriorates as you work down. This is my working theory anyway. As you can see in the diagram, 0 on our CRL setting, which is set as 5, wraps around anti-clockwise, making its way to 4, 3, 2, 1, 12, 11, 10, 9, and 8. 8 is the value of 9 on the CRL, and you can see that that uses all of our 1K resistors in series. That would mean that 0, which is 6, uses no resistors. The reason why I came up with that conclusion is I was using the dial as a reference and saying that because somehow we arrived at the right number, that somehow 9 was more closely aligned to the number we were looking for and therefore had the right value. That was incorrect. Everything else in my analysis is correct, only that to assume that because the value was closer on the dial meant that there were less resistors was wrong. So it tells me that these resistors are not half of 1%. If we look at the whole dial as a whole and see that what half of 1% would be as it equates to the secondary dial, and granted this is 120 gradicules, but if we were to just look at it as 1%, and within 1% would be 1 notch, half of 1% would be half of that. So even at 120, we would only really see deflection within 1 notch regardless of where we were on this dial here, which would be really good, but we're not. Our correction factor goes all the way from 0.01 positive to 0.06 negative for a total value of 7 dashes. So that's, from a long dash to a long dash plus 2. So that's an unacceptable amount. So we're going to have to get some precision resistors in here and fix this circuit here so that we could have this CRL multiplier be able to work without skewing the results every time we have to turn it, and make this more precise. Obviously that doesn't address anything else here. We're just talking about this one specific part. And so we begin our business going on Mauser and trying to find all of the resistors that we're looking for. Aside from the 1 ohm that I found in half of 1%, all of the other ones I was able to find in a 1/10 of 1%, which is pretty good. Could not find 9 ohm. 9 ohm was just not to be found. Combinations didn't seem very good. I'm probably going to have to look at a different source. 90 ohm wasn't found either. Excuse me. However, and neither was 550, but 550 is just a calibration resistor. I could find a different calibration resistor. But 90 was able to be found as a derivative of 80 and 10. I did look at the possibility of trying to find 180 and, dividing by 2. That didn't happen. But I did find some 0.01s for 80 and 10, so that was good. Obviously, while I'm doing this, I'm just bracing for electrolytics already. So I got the electrolytic part numbers as well, looked at what was in the chassis. I'd already been doing my homework on this, seeing what's what I'm going to ultimately need to do. The really important thing for the CRL, which is the topic, is that 1K. And I was able to source the 1K not at 0.5% as originally specified, but at a 1/10 of a percent. So that's pretty cool. So it's definitely, we're going to remove that unit. But this definitely closes out this movie. The next movie is going to be taking apart the chassis and cleaning it up. Getting that CRL dial out of there in preparation for refitting the resistors on there and whatnot. So this is a good breaking point. So thanks for watching. Stay tuned for more.